Welcome to the class again. We were discussing examining the spectra, IR spectra. Now we will discuss aromatic compounds. How do we identify the structure of toluene from IR spectra? As you know, we cannot identify the complete structure, but we can identify whether it is an aromatic ring or not, then whether it is having a mono substitution or di substitution. So these points we can identify, right? Right. So for aromatic ring, we do have sp3ch sp2ch stretching vibrations, so will be around 3050 centimeter inverse. Yeah, we do have them. At the same time, methyl group is having aliphatic sp3ch stretching vibrations. Yes, they were also observed below 3000. Then aromatic C double bond C stretching frequencies we will generally observe at 1450 and 1650. Yeah, we have those stretching vibrations. We cannot pinpoint them. Okay, right. Then another important point, OOP. For mono substitution, we do observe two peaks at 690 and 750. Yes, for mono substitution, we are observing 650 and 750. Sometimes we also observe these stretching vibrations for mono substitution from 1800 to 2000 centimeter inverse, but generally with the very less intensity. Okay. Now we will look at di substitution. As I said, we will have ortho di substitution, meta di substitution, and para di substitution. What is the difference between them? Right? Yeah, in this, for example, these two molecules are having same molecular formula, but this is other compound, this is meta compound, diethyl benzene. This is other diethyl benzene. So how do we identify, how do we differentiate them? Yes, they do have characteristic aliphatic CH stretching vibrations, aromatic CH stretching vibrations, at the same time C double bond C aromatic stretching vibrations. All these molecules, for example, look at these three molecules. This is meta and this is para. So all these molecules are having these C double bond C, aliphatic CH stretching vibrations, aromatic CH stretching vibrations. But how do we differentiate them? Right? As I said, we need to look for fingerprint region. Though the functional group region from 1500 to 4000, it may be same, but the fingerprint region 500 to 1500 will be different for these compounds. For example, ortho di substitution, we do get a single OOP peak at 750. Please look at this peak. This is at 750. From this, we can clearly say it is an ortho substitution. Then for meta substitution, we do get three peaks at 690, 780, 880. Yeah, we do have these three, 1, 2, 3. Yeah, these three peaks, they represent the OOP of meta di substitution. Just ignore the additional peaks. Okay, just ignore the additional peaks. Then for para, we do get only single peak more than 800, right? 800 to 850, yes. For ortho substitution, we get a single peak at 750. For para substitution, we get a single peak at more than 800. See, this is more than 800. So this is how we can differentiate the different compounds when we were given molecular structures, then differentiate them using IR. Yes, we can do that. Of course, for styrene, we have this unsaturated carbon hydrogen stretching vibrations, mono substitution. So it will be giving two peaks, 690 and 750. Then we have C double bond C peaks. For mono substitution, 1800 to 2000 low intensity peaks. Just ignore the other bands. Okay, so we cannot identify each and every peak in the IR spectrum. Just pick up what we need. So I'll quickly go through some more. Okay. Yeah. When we have alcohol, what is important? We need to look for this 3400, around 3400 broad OH stretching frequency. If it is hydrogen bonded, yes, we can clearly say it will give broad peak. If it is free, that means if it doesn't possess hydrogen bonding, then it will give a sharp peak. I'll give the differences also. Okay. Yeah, here also it is same thing. Yeah, for phenol also it gives the same broad peak. It is a para substitution, so more than 800 we will get OOP peak among other peaks. Right here you see the differences between hydrogen bonded OH and free OH. When we take a concentrated sample of the alcohol, obviously it possesses hydrogen bonding. So in a neat spectrum or in a concentrated solution, we do get hydrogen bonded. But in a diluted solution, yes, it is possible sometimes we may get hydrogen bonded, sometimes we may not get hydrogen bonded. So in that case, it gives a very sharp peak. This OH, it is free OH. So it doesn't involve in hydrogen bonding. Whereas this OH, this broad peak is for hydrogen bonded OH. If we still prepare further dilute solutions, then we doesn't have hydrogen bonding. This spectra is completely free of hydrogen bonded OH. See, very sharp OH stretching frequency around 3600, right? So free OH will appear around 3600. Hydrogen bonded will appear around 3300 to 3400. Methyl aryl ether, of course, it is a normal. Yeah, when we look at the carbonyl, 1810 and 1760 for anhydride bands, 1800 is acid chloride, 1735 is ester, 1725 is aldehyde, 1715 ketone, 1710 carboxylic acid, 1680 or 1690 is for amide C double bond O stretching frequencies. Now we will look at the influence of unsaturation. As we know, unsaturation leads to decrease in the bond strength. So as a result, the energy of the transition or vibration will also decrease. So in this case, because of this double bond unsaturated conjugation, what will happen? This is a ketone which we generally observe at around 1715 or 1710. But because of conjugation, its frequency is decreasing, right? So I'll give you a general rule. Whenever you have conjugation, you just decrease 30 to 20 centimeter inverse. Okay. For example, in this case, it is 25 centimeter inverse. Okay. Then you can see in all these examples, it will be around 25 centimeter inverse. So in exam also, they will give like this. So if you have conjugation, just decrease either 20 or 25 or 30. The range is from 20 to 30. So for simplicity, we will go for 20 or 25 or 30. Okay. So I always suggest either you go for 20 or you go for 30. So because of one double bond conjugation, you decrease 30, 1715 minus 30. So it will be 1685. So something like this. Because of aromatic conjugation, you decrease aldehyde will be around 1725 or 1730. You decrease around 30, then it will be around 1695 or 1700. Carboxylic acid will be around 1710, but because of aromatic conjugation, decrease 30. So it will be 1680. So something like this. Whenever you have conjugation, just decrease the frequency by either 30 or 20 sometimes. Okay. Mostly go for 30. First preference 30, second preference 25. Then this is an aldehyde. How do we identify aldehyde? As I said, a strong C double bond was reaching frequency around 1725. At the same time, CH, aldehyde CH will give a doublet. In this case, see, it is one peak is here, another peak is overlapped with the aliphatic CH vibrations. Okay, but yeah, it is clearly showing a hump here, right? So this small hump, you can say it is the doublet. Then a overtone with a weak intensity, generally double of this frequency, 1725 into 2, so around 1350, sorry, 3450. So it will be the overtone for that. Okay, then these are all aliphatic CH stretching vibrations which appear at less than 3000. This is the 3000 line, so they are below 3000. So when we look at the spectra, we can clearly identify them. This is unsaturated conjugated aldehyde, so that is why we are observing this peak at less than 1700, right? Maybe 1690 or something like this. Then because of the double bond, we also have sp2ch stretching vibrations more than 3000. Because of CH3, we do observe aliphatic CH vibrations. Then because of the aldehyde CH, we observe a doublet. So we are all we are observing all these characteristic peaks. Of course, as I said, we cannot identify each and every peak in IR, so just ignore the additional peaks. Similarly, for benzaldehyde, monosubstitution, 2 peaks 690 and 750. Just ignore the other peaks 690 and 750. Aromatic 1400 to 1600. C double bond because of conjugation will be less than 1700 or just near 1700. Then aromatic CH vibrations, aldehyde CH vibrations a doublet. In the ketone, we don't have that doublet. Aldehyde CH doublet will be missed here. Because of conjugation, yes, C double bond or stretching frequency will be less than 1700 centimeter inverse. Yeah, what I will do, these are all similar things. I'll just show the spectra. Here C double bond Y is there, aromatic is there, mono substitution is there, aromatic CH stretching vibrations more than 3000. So this is 3000, okay? So these are more than 3000. Aliphatic is also there, so it will appear less than 3000, aromatic more than 3000. When we look at the cyclohexanone, 1720, then aliphatic CH stretching, carbonyl overtone. As I said, just ignore the other bands. Just ignore the other bands. 1,3 diketone, it will exist in its tautomeric, it will be tautomerized to have enol form. So because of the enol, it also exhibits OH stretching frequency. If it doesn't exhibit enol form, then OH will be absent. But because of the tautomerization, it exhibits enol form. So that is why we will have OH stretching frequency. And we will have two C double bond O stretching frequencies. Enol, because of enol formation, it is single bond. So the bond order will be around 1.5. So that is why it is showing less frequency. This is for normal ketone, but still because of hydrogen bonding, its carbonyl stretching frequency will come down. Because of hydrogen bonding weakens the C double bond. So normal ketone will appear around 1710 or 1720, but because of this hydrogen bonding, its frequency may come down around 10 centimeter. Okay. So for carboxylic acids, we do observe a very broad peak from 3400 to 2400. Okay, so you cannot miss this. Of course, all other vibrations, like if you have aromatic CH or aliphatic CH vibrations, then alcohol OH stretching vibrations, all of them will be overlapped in this. So from the small bumps, we need to identify them. Otherwise, we cannot identify. Yeah, here also you see this peak, it is very, very broad. the esters, as I said, we will have C double bond of stretching at 1740. It is an overtone. Of course, others we can ignore. In this case, what happens because of the resonance, just decrease the 30, so it will be around 1710. So for ester, from 1742, it will come to 1710, something like this in case of conjugated ester. So just ignore other peaks. Yeah, when we have vinyl group on oxygen, as I said, it acts as a withdrawing group. So in that case, C double bond was stretching frequency increases. When you increase that, you also increase by 30. So 1740 plus 30, around 1770. So this is around 1770. Of course, C double bond C is also there. Okay. So I'm not discussing all other stretching vibrations. You just concentrate on these two. So when you are decreasing the frequency because of conjugation, decrease by 30. When you are increasing the conjugation frequency due to withdrawing groups, increase by 30. Okay. You can make it as a rule of thumb. Aromatic ester, because of aromatic, it will decrease its frequency by 30. So here it is around 1710. Methyl salicylate, additionally, other than conjugation, it is also having hydrogen bond. So because of the hydrogen bond, C double bond was stretching frequency will further come down. So it will be around 1790 or 1780 in this case. So because of aromatic nature, its C double bond was stretching frequency is decreasing by 30. Because of hydrogen bond, you can also decrease the C double bond of stretching frequency by 20. Yeah, here you can clearly say for normal 1740, for conjugation or withdrawing group present on oxygen increase by 30, so 1770. For conjugation to carbonyl decrease by 30, 1740, so it will be around 1710. So go for that. Okay, increase by 30, decrease by 30. Yeah, for amides, apart from the C double bond O, we also have, because two hydrogens are present on nitrogen, so we will get a doublet here around 3400 centimeter inverse. Then of course NHOOP, a very broad OOP. This also we will identify it. Similarly, if it is a single hydrogen on nitrogen, we will get a sharp peak if it doesn't possess hydrogen bonding. If it possesses hydrogen bonding, we will get a broad peak. So it is based on hydrogen bonding. So it is similar to OH. NH peak is similar to OH. Of course, this NHOOP, we cannot miss this. So I'm not giving details for all. Yeah, you can, we have discussed it, right? For 6, with the decrease in size, lactams, the double bond strength will increase, so the frequency will also increase. Acid chlorides, it is around 1800 C double bond O. So for anhydrates and acid chlorides only, it is 1800. For all other things, it will be less than 1740. Okay. Acid chlorides, I'll just skip. Even anhydrates also, we will get two peaks for anhydrates, so we cannot miss them if it is an anhydrate. Normal amine, for normal amine also we will get a doublet if nitrogen possesses two hydrogens. And NHOOP, a broad OOP. Yeah, here see if nitrogen is having single hydrogen, dibutylamine, NN dibutylamine, so it will have only one hydrogen on the nitrogen. So because of that, it is giving a sharp peak. Of course, amine peaks are less intense, so they appear around weak to medium intensity, whereas alcohol peaks, they are very strong, right? Alcohol peaks are strong, but amine peaks are medium to weak to medium in intensity. NHOOP. if it doesn't have, if it is a tertiary amine, if three alkyl groups are there, we don't have that NH stretching vibration. We have one hydrogen and nitrogen, so we are getting a sharp peak. If it is a triple bond, yes, 2250, we will get a stretching vibration. So if it is a C triple bond C, it is 2250. If it is C triple bond N, nitrile group, it is 2250. Yeah, here also it is a monosubstituted aromatic system, aromatic CN, then CH, aromatic CH. Another important point is thiols. Thiols also will give its characteristic absorption peak around 2500 centimeter inverse. SH bond will appear at 2500. Halogens generally appear less than 1000. So you just go for them, okay? Yeah. Uh, just look at these examples. We will try to solve them. A compound having molecular formula C7H9N and its IR spectrum was also given. Then what is the compound? What is the given compound? So molecular formula was given. Molecular formula was given, so we can easily identify it, right? IR spectra is given, molecular formula is given, we can identify it, right? How do I identify them? You know, when we were given molecular formula, first go for double bond equivalence, degree of unsaturation. Now, for example, for each double bond, we need to reduce two hydrogens from the alkane formula. Alkane formula CnH2n plus 2. In this case, it is C7. So if it is an N alkane, it should have 16. 2 into 7 plus 2, 16 hydrogens. Whereas it is having only 9 hydrogens. In the case of nitrogen, if you want to calculate degree of unsaturation, you need to decrease one more proton. You need to decrease one more proton. So for normal alkane C7, it should have 16 hydrogens. And here we have only 9 hydrogens. Because it is a nitrogen, you just decrease 1. So 8 only. 16 by minus 8, 8. 8 by 2, 4. So that means degree of unsaturation is 4. Generally, this 4 is for benzene ring. Benzene ring, we have 3 double bonds and 1 cycle. So altogether, it will have a 4 degree of unsaturation. So if you are given C7H9N, just take the benzene ring C6. Then we also have one more carbon. Then, yeah, whether it is mono substitution or di substitution, just go for this. We are clearly having this 690 and 750. That means it is mono substitution only. 690 and 750. So it is mono substitution, right? If it is having carbon attached to benzene and then nitrogen, that means NH2, or another possibility is nitrogen attached to benzene ring, then methyl group on nitrogen, so that nitrogen will have only one hydrogen. There are two possibilities. Among the two possibilities, you see this nitrogen hydrogen bond vibrations, it is giving a doublet. Doublet means nitrogen possesses two hydrogens. So altogether, what we can say, benzene ring, then carbon is attached to benzene ring, then it is having amine. Okay, so this is how we need to identify the given organic compounds. When we look at this spectrum, we can clearly say it is an alcohol, right? It is an alcohol. And go for a double bond unsaturation. If it is giving degree of unsaturation 4 or more than 4, then it is an aromatic system. In that case, look for substitution. Okay, we have 3 peaks here, 690, 780, 880. So go for that. The below one is it is an alcohol. So by just looking at the characteristics, we can clearly say whether it is a, yeah, in this case it is 1718, that means it is ketone. It is purely a ketone, because ketones will give you around 1720. Yeah, in this case, you see this is nitrile peak. This is nitrile peak. Yeah, we were given two aldehydes. One is conjugated aldehyde, one is unconjugated aldehyde. So the C double bond of stretching frequency was also given 1720. Then what is your answer? Whether it is conjugated aldehyde or unconjugated aldehyde? A cinnamon oil C9H8O. Then what is the formula? Formula was given. Then what is the structure of this compound? From the degree of unsaturation, we can say it is having an aromatic. So 9 into 2, 20. Out of 20, we have 8 only. So it should be 6. So degree of unsaturation 6. Out of 6, 4 will be going for aromatic benzene ring. And you see, here we have two groups, 690 and 750. So it is mono substitution only, right? 690 and 750. So it is aromatic system, mono substitution. And yeah, we have 1677. Say for example, if it is a ketone, it should appear around 1710 or 1720. Because of aromatic conjugation, what we think we need to decrease 30. So we'll be around 1680, right? At the same time, double bond conjugation is 6. So 4 for aromatic ring, 1 for carbonyl, one more will be there. One more is double bond. One more is double bond. So in this case, it is a trans cinnamaldehyde. It is a trans cinnamol aldehyde. Okay, so that is why we do have less OOP for trans. Then because of conjugation, it is decreasing. Then it is mono substitution. So that is why it is giving two peaks at 690 and 750. This is how we need to approach. Calculate degree of unsaturation and go for it. Then which one is cis and which one is trans? Among these two, one compound is trans, cis and trans, 3-hexene, 1-ol. Alcohols, both are alcohols. Yeah, you can clearly see functional group is more or less same, but fingerprint region is entirely different. Now you tell me which one is cis, which one is trans. Please unmute yourself and convey your answer. Let me explain. This is cis, this is trans. The trans will give very less intensity. Cis stretching will give a medium intensity. At the same time, here cis OOP will be around 700 or 800. Trans OOP will be around 900. So from this we can clearly say whether it is cis or trans. Now, among these, the given spectra belongs to which compound? The given spectra belongs to which compound? As I said, take the reference. it is normal 1720 or 1710, something like this, 1720. Okay, we will go for it. Then when we decrease the size, its frequency increases. As I said, increase by 30, 1720, 1750, 1780, 1810. So given 1780, that means it is C. It is C. So just remember this, increase by 30 or decrease by 30. Then you can easily answer them. Yeah, here also. You just look at the spectrum and identify the correct compound. It is 1688. That means it is conjugated carbonyl. In this case, it is not conjugated. It is not conjugated, and it is even not carboxylic acid. In this case, it is not conjugated. In this case, it is conjugated. So 1688 resembles conjugated carbonyl, right? So the answer is A. Yeah, C triple bond C and CH stretching vibrations. Yeah, that's all what I want to convey to you.